Alright, today we're going to talk about a calculus theorem that you probably realize that it makes sense, and you've probably used it a ton of times, but you haven't thought about it in mathematical terms. So, for example, let me read you a word problem. If policewoman Betsy sees me at the corner of Humboldt and Emerson Avenues in Minneapolis at precisely 12 noon, and then her husband, policeman Bubba, sees me 60 miles away at the corner of Grand and Fairview Avenues in St. Paul at precisely 1 p.m., can they give me a speeding ticket? Well, you can figure that out by the distance and figure out what the speed limits are and know if they've done that or not. For example, if you know that it was 50 miles from one of those locations to the other, and you know it took an hour to get there, then you know you were going an average of 50 miles per hour, which meant at some point you had to be traveling 50 miles per hour. And if the speed limit on all those roads was 40 miles an hour, then of course they could give you a ticket. Now, the fact that we know the average, and we know that means that we have to travel that at some time, is actually a calculus theorem. It's called the mean value theorem. This is section 4.2 in your book. And the mean value theorem says, if you have a function and it's continuous on a closed interval, remember a closed interval means that it includes the endpoints, and it's differentiable on the open interval, then there is at least one point C in this open interval at which the derivative equals the slope of the secant line. Now remember, the slope of the secant line is an average. So if we have, let's say we have a function that looks like this, and we're going from A to B. Then the secant line goes from this point to this point, and the slope of this line is this right here, because we've got this is our y value, f at A, and our y value, f at B. So we take the difference of the y's over the difference of the x's and we get our slope. Well, what this theorem says is there has to be some point along this curve, some point C, let's call it, where the tangent line has the same slope. The tangent line is parallel to the secant line. There has to be some point along there. And that word problem we just talked about is something where we would use that, where we would say this average, remember the secant is an average rate of change. The average, some point along the line, the instantaneous has to equal the average, just like our average speed. At some point along the line, we had to equal that average speed because it was a smooth, you smooth acceleration, smooth deceleration. So that's the mean value theorem. That's all it is. Make sure you know the qualifications. Continuous on the closed interval, differentiable on the open interval. Then you've got this that happens. Think about this for a few minutes and make sure you've got that. Now, we've talked about a little bit when we were looking at maximums and minimums about the derivative, increasing and decreasing. So let's kind of review that a little bit just to make sure we've got it. If we have this function here, we know that at a maximum like this, we know the derivative equals 0. The slope of the tangent line equals 0. And what did we say about the slope here? Right, we said it had to be positive because f of x is increasing, and so it had to be positive. And then over here, our function is decreasing. What does that tell us about our derivative? That's right, it's negative because f of x is decreasing. So hopefully you remember that from where we talked about the extremes. So that was just a little review. This section is kind of a mishmash. So we got the mean value theorem, review this increasing and decreasing, and then there's one last thing that we're going to introduce that's kind of pivotal to the second half of calculus. If we have a derivative f prime of x and it's equal to another derivative g prime of x at every point on an interval, let's just call it I. Then there is a constant c such that the actual function is equal to the other function plus some constant for every x contained in the interval I. So basically, what does this say? This says if the slopes of the tangent lines are the same, then those tangents have to be parallel, which means that the functions are about the same. So what you have is, if you've got some function f of x, and we know that f prime at x equals g prime at x, then g is the same looking function. It's just moved up or down some. That's all it means, because look at these tangent lines. We've got a tangent line here on f, and we look at the same place on g, and the tangent lines, if I could draw a straight line, would be parallel. So same type of thing. Now, why is that important? Well, what it means is if you have derivatives that are equal, then you have multiple functions that they could come from. So you could have a function x squared plus 2, and it's going to have the same derivative as the function just x squared. Now, how is that helpful? Well, because we need to be able to find antiderivatives. Antiderivatives are just what they sound like. It's opposite. It's undoing the derivative. An antiderivative, we'll call it f of x capital if the derivative of that is equal to some function f of x for every x in the domain of f. So this is the antiderivative if its derivative is equal to the function. Now, that sounds like a lot of jumbly mess, so let's try one just to make sure we understand what's going on. When you're finding this, it's called antidifferentiation. And so let's look at an example. If we know the acceleration of a falling body is 32 feet per second squared, that's gravity, and it falls from rest, and we want to find its velocity function and its position function, well, we know that velocity is the derivative of position and acceleration is the derivative of velocity. We found them all from position, but what if we have to go backwards? Well, if you were to take the derivative of something and you end up with just 32, then what would you think you would be taking the derivative of? Right, you would have 32t, because if we take the derivative of that, we're just going to get 32. But what we have to keep in mind is if we have some constant, a number, its derivative is 0. So when we took the derivative, it went away. So we have this plus c that we have to deal with. Now, if I told you that the body started falling from rest, that would mean that v at 0 was equal to 0. And so what you would have to do is you would plug in 0 here. So we have v at 0 equals 32 times 0 plus c. So we have 0 equals c. So that means that our v of t is just equal to 32t. But you have to solve for this c using an initial value or something else given in the problem so you know what the c is. Now again, if we want to go from 32t and figure out what we took the derivative of to get there, well, we know we're going to go up a power. But what would happen here? Well, when we take the derivative, remember we bring it down, so we multiply times 2. So we need something we're going to multiply times 2 and end up with 32, and that's 16. So we have 16t squared. And again, we've got to have this plus c, because if we take the derivative of a constant, it's going to be 0. I told you it fell from rest, so and our initial position is going to be 0. So again, we plug in 0 here and solve, and we see that c is also equal to 0 in this case. And so we have our functions. Now, when you have these, you either have to leave the plus c in there, or you have to use some information from the problem to solve for c, okay, if it's given. If it's given, then you solve for c every time. If it's not given, you leave the plus c there because we don't know what that could be. So antiderivatives, antidifferentiation is just working backwards from the derivatives. So read over this section, make sure you understand about the mean value theorem. You remember about what happens with the derivative when a function is increasing or decreasing, or a maximum or a minimum. And then we need to start working on antidifferentiation. Write down any questions you have so that you can ask them in class.